Okay. So we continue on statistical mechanics from the previous lecture. We haven't finished the calculation yet for the example of the classical gas, right? So I believe that so far we have this quantity, omega bar, right? Which is after you did all the integration, and what you're going to get is okay. Similarly, so once you have this quantity, it's not difficult now to compute the omega, right? Because we know that the relation between the omega and the omega bar. So your omega is going to be this one. Did I give you a new set of homework? Did I? For this thermodynamics from last week?
I think yes. Yeah.
All right. Okay. Good. Okay. I'm still confused myself. Actually, did I give? I'm not really sure that I give you a homework. Okay. So this is your omega, and then so we consider this limit, large number limit. Okay, so your omega can be approximate into this form. Appreciate. All right, so we have this one. Once you have this, you could compute the entropy. So next, you compute entropy. Which is this one. Okay. Okay, taking this form. I believe that you understand this notation, right? The trace, right? And this rho is density. Okay. And so actually, from the previous class, we know that the way that we define the density metric, right? So then we put this is the Boltzmann constant, okay? Okay. Let work out. So here you put the rho in your entropy, right? And since you put this rho into the logarithm function, is now a constant, so you could take it out from the trace. So what you're going to have is this one, trace of the rho. Okay, are you okay with this? The reason why I can take this whole term out because it's just constant now, right? Okay, so what you need to do is that you need to compute this term, trace of the rho, right? So, and well, since okay, not go. So we recalling a plot condition, right? It actually must be 1, right? Right. Then it means that so this term is going to give you 1 because the trace of the rho must be 1, right? Otherwise, it's not going to satisfy that. So then you get now this quantity at your as your entropy. So beside that, so this entropy proportional to the log of this quantity, right? Which is this, it could be said is accessible space volume. Okay, and with the limit of large n, so you're going to have actually this one could be expressed in terms of this omega bar. Okay, if you do the expansion, if you use the relation that we have here, actually here, right? If you look at this, so. Or so we just ignore ignore this is, oops, sorry. All right, so it means now that this this whole term is going to be the same with this logarithm of the omega bar, right? Then the entropy could take the form of the omega bar, okay, which is plus, okay, this is your entropy, right? This is for the classical gas, okay. So let now let the total energy is the same within the internal energy of the system. Okay, then you're going to have okay, you're going to have this relation. And so then you can find of course that you could compute the temperature of your system by using this quantity, this relation that actually you fix the volume and the number of particles in your system, right? And you consider the partial derivative of the internal energy with respect to the entropy, which is actually we derive it from this from the Maxwell, right? Yeah. So what you're going to have is this one. Okay, which it give you. Oh, all right. Is it familiar?
Yeah, yeah.
Oh. Yeah, it's going to be 2/3. Sorry about this. So, well, this is kind of the standard quantity of the energy. The reason we have this number because this is actually so they depend on the degree of freedom, right? Right, and then we say that according to the equipartition, right, theorem. So each of the degree of freedom have the same amount of energy, right? Okay. So then with this, so you could also compute some other quantity as well, like pressure. Suppose we compute pressure. So with respect to your volume, and you fix these two. So you're going to have here. So what you get is this one. Again, this is classical gas equation right here, equation of the classical gas. Next, you could also compute the chemical potential, right, with respect to the change of the number of particles that getting in or getting out of the system. So you're going to have this okay. Okay, this is what we have. Okay, so let's draw the diagram of this classical gas, right? So if you look at the PV diagram, so you're going to have this kind of curve, right? All of this called isotherm, right here, which is they are constant right here. The process actually moves along this line on this diagram, right? Is going to be constant in temperature, right? Okay, and so if you draw the T and V diagram, so you could get this. This is called isobar, right? You could have this kind of thing, okay? Because T and V, if you could show, actually it's a linear, right? This is T and V. If you move P to be this is just the slope, right? Okay. And the last one, which is going to be T with the P. Again, you're going to have this, right? This kind of curve. Okay. And so if you put this 2D graph together, right, you're going to have this. I think you've seen this before. This graph I probably draw it already in the previous class. Okay. So you're going to have this. Okay. I should use different color. Let me put here. Okay. T constant. Because this nothing but isobar. Okay. Oh no, isotherm. Sorry for that. And you also could have this Okay. And this. Okay. This is P constant. This is V constant. Okay. So, and then you have this as a P, and this is V, and this T. Okay. So you have 2D surface. Okay. So what you have is that 2D surface here, right? We should represent the process that you could actually you could do with the classical gas, right? And again, as I may probably explained to you earlier, there must be kind of part independent feature for any thermodynamic functions, right? If you like, if you start here as the initial point, and this point might be your final point, there might be a part right here, right? And then you could do something else to get into this point, right? And then you could find actually the total difference of the U, which is actually solely depend on the function at the initial and the final point, not really depend on the part. Okay, that is the part. Independent feature, which is actually we get this from the Maxwell relation, that kind of thing, and then I also give you the idea how to construct or how to capture this part independent in terms of the action principle, right? Okay. Okay. I think that's it for the microcanonical. Next is going to be canonical ensemble, but I'm going to stop here and then we get back to the thermodynamics a bit because so far we deal with classical gas, but we need more realistic thing like a real gas, but not that kind of really real gas, but we're going to do some kind of approximation anyway, because otherwise then your calculation is going to be really, really difficult. But anyway, let's see what we could do with this kind of situation. Where's my white chalk? Here. Okay. All right, so now get back to thermal a bit for your gas. Right here. Or non-radial classical gas. Okay. So we consider a mono and identical Okay, so we have this kind of monoatomic gas with n identical particle with mass m in the container with the volume V at temp T, right? And now let this be density which is very low. We need this condition to make sure that actually thing will be classical. Right. All right. Okay. Then the Hamiltonian. Suppose that, okay, let's draw a picture first. Suppose I have a container, which is actually in this case is a box. It's a stupid box here, okay? And you have a bunch of gas that's spreading around in this box. Okay, okay. Okay, so let if I take this point as the origin point right here, so and then I say that, okay, this is the particle K, and this is another particle J. So I could draw a position vector, right, which is I will call K, and so this is going to be J, right? And so this, I have also another vector, which is actually, but I'm going to consider only the magnitude of it. So it's going to be this one, Rij, because I just need only the magnitude, the range of this. Okay. Then, so the Hamiltonian, suppose the Hamiltonian is going to be these two parts, the kinetic plus the potential, right? This is also include, this potential include interaction, right? Okay. And so for the kinetic is very simple. You could say that actually you have this, okay? But for the potential is a bit tricky, right? Next, we introduce I introduce this to JK, right? Which is the function that actually depends on the range of the two mole or two particles, JK. Okay. Be going to be introduce, oh no, to be the interaction okay, these two particles, J and K, then it is just a pair, right? This is just a pair between J and K. So it means that if you need to include all possible interaction, you need, of course, that you need to consider something like this. Here. Okay. And I can put this this is kind of this is a highly redundant term. So we have to take care that actually you consider only one term. It means that you have to put this inequality into this. And of course that if you don't want to put this inequality, you can divide by half of it, right? Because if you, after you consider all the possible pair, and then you take out all the leader than term, it's just half of it actually survive, right? Now, J not equal to the K, right? Okay. And so this it is strongly repulsive when the particle are very close, okay? Because otherwise, then your particle will bump into each other, right? We don't want to that. We don't want that kind of situation because we just need that kind actually when it get very close to each other, it just splitting. I mean, in this way, and is it weak, attractive at large separation. Okay, so it means that when your two particles are very far away from each other, it's not going to attract, feel each other, that kind of way, and in a very strong sense, that kind of thing, that the condition that we want. Then with this condition that we want to then we write, I would say, okay, this kind of potential and if you plot a graph, you will get this kind of graph. If you look at this, if it's very, very far away, your potential is going to be very weak, right? And if it's very close to each other, it's going to be very, very strong. Okay, that actually satisfies our condition. So then this is called Lennard-Jones potential. You might probably heard of it before. Anyway, this kind of potential is still difficult to deal with. However, it's still difficult to deal with. Then we make it simpler, okay, by consider this type of potential this is okay. So in this area, the potential is infinity, right? In this shaded area. So this means that a minimum possible separation between the particle is R0. Right. So if you could think that actually the radius of the particle that you consider is R0 half, then another one is R0 half. Then this is the closest that two particles could be, could be sit together. It cannot be get closer more than this. That is the thing. Okay, so now I think this kind of potential is better than this one, because it's, you see it's kind of look more friendly than that one. Okay, so next we compute the partition function, which is, I believe I haven't introduced you yet, right, about this partition function, but okay, let's just work with it at the moment, and then later I'm going to introduce you this kind of function later in the StatMath context, okay? And then I'm going to give you also the physical meaning of this function. Okay. This n factorial, we put it here, taking into account the indistinguishable or in simple words, they are all the same. Then you cannot see the difference between this kind of group of particles. They are all the same, right? And that is the reason why we have to take in this factor into account. Okay. And so you need, what you need to do is that you see that actually this is the kinetic term and the potential term. And the kinetic term is very easy to deal with because it's just the Gaussian integration. We can do it right away. But you still need to think about how to do the integration for the potential term. Anyway, after you finish the integration with respect to the p, right, you will get this. Well, here, beta is 1 over kBT at the moment. And you have set V, where set V is this whole bit here. Okay. And of course that this integration can be done or not depends solely on what kind of function that you have here, right? It's not, there is nothing guaranteed that you're going to do the integration, right? So we now consider limit so the limit right here, if we took beta to be 0, what does it mean? That it means that your temperature is very high, right? Very high. So we have high temp, right? High temp. So your set V can be approximately into this just e to the power n, right? At this limit, I mean, at this limit, you will get this, right? Now, next, we consider the expectation value of this internal energy. You know that how to do this kind of computation, right? Because we did that before. Okay, and then do dy. Okay, so it's turned out to be this quantity. Agree? Well, you could prove it yourself, because if you take this set V, right, and you do the logarithm, you take the the logarithm function here, and you do the partial derivative with respect to the beta here, right? You will get this quantity with that function, but I'm not going to do it for you because it's not difficult. Okay. But okay, after you have this, so then so right. So we put this term since at 0. Right. So we know that if you put beta here to be 0, you have to get this one. It means that if you put beta here to be 0, this term will be vanished, and then you have to get this term there in order to satisfy that limit. Okay, is that clear? Okay. All right, then next, okay, from sorry, this is should be V. Right. So actually, this sorry, this should be V, not U, because I use different notation here. Right. Should be V, not U. Right. Okay. Sorry about this. So you find that actually the expectation value of this could be actually written in terms of little u here. Oh, yeah, right. Yes. Yeah. Sorry. Okay. And you could do the approximation, right? You get that if n it very, yeah. And oh, okay. This u, this little u here. We should actually, again, you could put in terms of the partial derivative with respect to the beta, and of course, this one, right? Now we need to deal with the integration with respect to that small u, right? So what I did is I just put 1 and minus 1, which is actually 0, right? Nothing there, right? But this could give you a trick, actually. All right. It's going to give you this. All right. Now it's going to be confused because this V going to be volume. Let's put it to be this. Okay. Volume. All right. You could take this volume out, and I is this integration. All right. We should you can turn it to be using by you can use the spherical coordinate, right? So once you use the physics, the spherical coordinate, all the angular part, after you do the integration, you will get this 4 pi r square, right? Okay. And then now it's not the difficult now to see, actually. This term is very small. I mean, very small. Which means that is very less than the volume, right? Sorry about my notation because I used V as a potential. I shouldn't, but I did that and I could not change. Now we have to keep going with this kind of weird V here. Okay. All right, then if you look at this, right here. So if you take a log of this thing, right, you will get that two terms add up to each other. And this is the constant, right? And then you get 0. And so this, you're going to get this, if you do the expansion, right here. So at the end, you will get as expression of this small u. Then the expectation of this potential is going to be 1/2 n square this V. All right, this one. Okay. Now we kind of not done yet. We have to keep going a bit to see. So if you consider this log of this function, I think yeah, let's see. I think this should be this kind of weird V, not potential one, but the volume. Right? Can you change? Can you go back and change yourself on by yourself in your note? Actually, sorry about this because I confused myself a bit. Okay. This term can be can be done easily right here, which is I0 is 0, then which is a function of beta is going to be okay, this one. So next, we compute the expectation value of this P. You're going to have and yeah. Okay. It's not difficult to see that actually what you're going to get. So let me write down again the result. And over V n square, right? This is what we have here, right? So, well, since this small n that actually we define like this, right? But you have to go back again to change the volume notation to be this kind of weird V to make it different from the potential actually function. Sorry about this one, but I make a mess for you. But sorry. So if you look at this, you see that actually the first term go with the power 1. Right? The second term is something to go with the power 2. It means that in general, it's going to be like a power series of this ratio and over V, though in general. In general, one could have so I change beta to be KBT, right? Then so you could have like an infinite series of this n, right? And now you could see that actually from this you could see some kind of interesting feature. There is okay, interesting feature. It turned out that for ideal gas. Right. We find that B2, B3 have to be 0. All the coefficient, I mean B2, B3 must be vanished. Then you get which is right, this one. Okay, which is the equation for the ideal gas. Oh, right, okay, well, yeah. Yes, you can put, of course, then. Of course. For this situation, right, your B2 is minus half I, right, which is and so we're going to use this kind of potential. Okay? We're going to use this kind of potential. So this can be split into two parts. You integrate from 0 to 0, but on this shaded area, your u is infinity, then it's left only minus 1, and then you get plus 1. Okay? And then here you get what you have from R0 to infinity. โอ้หิวข้าว Sorry about this but หิวจริง Okay, so okay, so if you look at this, this is not difficult. For this one, the minimum value of the u is going to be u naught here, u0 here, right? Then, so okay, let's assume. If we assume this condition at high temp, right, then this u, of course, you can do the expansion now, right? Right. Because if it's high temp, it means that this term is going to be very small, right? You can do the expansion. Once you do the expansion, so then you can do this integration, of course. Then your B2 is going to be half 0 third 2 pi and then so this actually you have to take this u to be u0, this term, right? Because this term is explain this kind of curve. All right, okay. After you do the integration, oh, so long computation, what you have is this. Okay, which is I'm going to put to be V palm. Okay. So then, for this, I mean, this kind of non-ideal gas with this simple potential, right? With you have to keep in mind that actually the potential we're working with is this one, not the Lennard-Jones one. Okay. But anyway, with this one, we get you have this one, and n squared. Okay. Mm-hmm. And then we can do approximation in this way. You know that we can do the what is this binomial expansion, right? Okay. If this one is very small compared to this one, so then this is like the first order of expansion, right? Yeah. Okay, then what you have is this equation. Woo. Okay, which is known as the van der Waals. equation. Okay. I believe that actually you probably come across with this equation even in the high school, right? I believe, but they don't show you how to get it. That well, you see the reason why they did not show you any detail how to derive this equation, because it's very a long calculation. Yeah. And so if we let this small v as let this number of mole of gas. Okay, if we introduce this kind of new symbol, then so this small n, right, could be expressed in terms of Na and small v, right? Na is nothing but Avogadro number, right? So your van der Waals equation could be now expressed in this RT, right? Where this new A is this one and new B is this one. Okay, that's it. Okay, then we get a usual van der Waals equation. It would be, I would say this is a standard, right? A standard form. Okay. Next, we're going to look at the critical. Next, we compute critical value, right? If we would like to see the critical value of the P, right? I mean, this TCs mean that make this value to be critical thing. So you will get okay. And we could also compute the second order of this, right? And we get Let's call this Gauss equation, and then this is Gauss equation. So if we consider the ratio between these two, so you will get then you could solve for B. And then once you solve for B, then you could solve for TC, which is and of course that you could solve for PC, which is actually okay. It's not difficult to do this, but I skip a lot of steps. Right. Okay, so here come to the final part, the last part of this non-classical, non-ideal classical gas. So for the classical gas, if we have a PV diagram, right? So you have this kind of curve. Oh, sorry, this is a bit strange. Yeah, right. It's not that kind of realistic. Let me polish it a little bit. Okay, so you have this. This is the line for the isotherm that we have in the classical gas. But for the situation that we consider here, what you have is that this kind of graph. Oh. Oh. Oh yes, I'm right. Great. Okay. I think I'm yes. It might not really in the scale, but I hope that it's going to be okay. Yes. Okay, you're going to have this kind of curve, right? From that equation, I mean van der Waals equation, right? And this point that actually give you critical, right? Okay. And you're going to have this kind of curve. Oh no, not this point. Actually, it's going to be this one. Oh, sorry, it's getting messy again. It's really difficult to draw by hand. Anyway, this C is critical. And down here, you're going to have a curve like this. Okay. Which is down here, your T is less than 3 critical. And up there, you're going to have the line that actually come to touch this point, okay, which is I shall call this TC, and you're going to have the line that go actually T greater than TC, right? I think I need to fix this again to make sure that, okay, so, okay. Okay. This is not the line. The graph should go something like this. Should go something. But actually, you could Google yourself later. But sorry, my drawing is pretty bad here. Okay. This area would call the liquid fit. All right. And this whole area would be liquid plus vapor, and above that would be a vapor phase. Okay, this is going to be the thing. I again need to change to make it more realistic. It should be something like this, because otherwise the graph is going to sharp. I mean, this second point. So you have this area, right, and this area, yeah. We find that actually this would be the minimum, right? And if you look at this, the whole area here, you will find that is less than 0, which is, oh no, it's greater than 0, which is wrong, right? We don't want it. Because why we don't want it? Because from the experiment, this is experiment, the graph of this PV is going to be like this. You probably see this kind of thing, right? Okay. Okay, this is again critical. Again, this is the real graph that we obtained from the experiment. And then if you compare these two graphs together, then there is a problem here, because inside this curve here is the change of the P with respect to the V must be constant. Then it's contradict. Okay, then this equation has a limit, right? Right, then let me point out again here before we stop. Yeah, I think okay. So you might have you might have a question actually, how to get this graph. I mean, do you know how could we get this graph? The graph that I do this. Well, since if you could solve P in terms of the V, you will get three solutions. Right. That is the reason why we have 3 points here. Right. That kind of thing. And so, and the thing is that actually we have to note that the area here and the area here are the same. But my writing, well, my drawing is okay. Make sure to make it more accurate. That it might be, yeah, it should be the same, right? So it means that, so the question is that how to get this kind of curve C, right? How to get a curve this, right? So what we could do is that, so if you label, if you say that, okay, you're going to consider this P, right? You're going to have a curve like this, right? And then you go up again here to be a new P here. Again, you're going to have a curve like this, right? And then you go up again. You're going to have a curve maybe like, maybe like this. And then you find out actually your C, your curve C go up here and go down there. It should, well, sorry about this. You should cut there, and then that is that is the way we get the curve C. And then the this point is a critical point. Yeah. Okay, are we good here? This is the way. All right. So, well, so again, this this is very far from the real gas, really real gas, right? And so at very high temperature, it's going to behave the same. Okay. Let me draw this out. These two at high temp will behave similarly, I would say. Similar, right? Okay. And here as well, not only, but after the critical point, but for this, I mean, after the critical point, they are going to be the same, right? you cannot use this van der Waals equation to explain the ideal gas at temperature lower than the critical temperature, because it's going to give you a wrong behavior, right? You see that actually the thing inside here is not the same with this. And again, yeah, you see the map, right? Okay, right. All right, okay, I think I stop here. Any question that you would like to ask? So, and then next class we're going to resume on the statistical mechanics. But I hope that you could see this kind of thing, the limit of this ideal gas, and the limit even we could try to do things a little bit more complicated, but it's still far from the real situation, right? Yeah. But I think, well, I'm not really sure that we might have another equation that actually would give you the behavior of the gas, which is actually may be very close to the real one. I mean. Mm-hmm.
We know we use this equation.
Say.
ก็คือเสกมาเลยอ่ะ
Yes, we know that if you want some certain area that is going to push very hard to each other when it get closer, right? You try to draw the graph first. That is the thing, and then
just
yeah,
just
and
try
then
to write.
and then you try to write out what equation that actually fit that curve.
Okay.
Is that clear? That is the reason why I call saying it might be, I'm not sure, it might possibly be a reason behind that, but what I understand is that it just fit, you just draw a graph and fit the curve. Yeah, and then you get the equation. Okay, that's it for today, and then see you next.